starting with a section on aldehydes and ketones. So these are talked about together always as a group because their structure is very similar. They both have a functional group of a carbon atom doubly bonded to an oxygen atom, and this is called a carbonyl group. And it would be drawn like this. Okay, that's the carbonyl group. For the aldehydes, very simply, we can stick a hydrogen on each side here, and we get something that you've probably heard of before. And this would be formaldehyde. Now, that's not the IUPAC naming formula. This is the old common name. And for a lot of these, we get into the aldehydes, ketones, we get carboxylic acids. Uh, common names are it. Okay, you're going to know them by carbon names. Part of why this is an introductory, you know, surface touching overview thing, trying to not get into too much detail with stuff of organic chemistry. So, um, I'm not going to ask you to name these uh, larger, or I don't know, not so much larger molecules, but some of the molecules where the common names are more common than the actual naming practice names since we adopted that later. But this is one carbon, so it's meth, and the aldehyde takes the al, not all like alcohol, but al name. The aldehyde takes the al name. So this is just going to be methanal, would be its actual IUPAC name. Okay, so quite different from its traditional name. In general, the aldehyde group, as you can see on that inside of your back cover of your book, where we've got the basic structures. Your basic structure pattern is this. You've got this carbonyl group with carbons there, some carbon. Um, so we could have one carbon with its 3 hydrogens off of it. Okay, we could have another carbon. Okay, some branch chain mess. We could have a ring. Any type of ring, I think, could have a carbonyl group on it. So the possibilities here are numerous, and that's why it's usually just designated as a, if you're talking about generic aldehyde structure, we have an R to represent all that variability, all that possibility. Okay, so that's what you need to look for. Structures I give you on a test and say, put these into their grouping, classify. Okay, classify these organic molecules. And so you're looking for this with some type of carbon structure over here. Ketones are a carbonyl group with 2 hydrocarbons attached. So back to our, and again, you'll see here shortly why these are talked about together. So here's our carbonyl group. Okay. And then instead of having hydrogen here, we're going to have carbons, 1 or more carbon structures. Over here again, the same 1 or more carbon structures that we had for aldehydes. So the difference between in structure when you're looking for patterns, the difference between an aldehyde and a ketone is an aldehyde with an R group on this side instead of hydrogen there. Okay, so they're kind of built on each other if you want to look at it that way. And I think if you read in your book, it actually goes through how you can do reactions to react one to get the other, and it's really cool and neat stuff. But it's just the scope of this class is not such that we can get into that type of detail with this. And I hesitated in the previous lecture. If you I paused a lot and sighed a bit, I noticed when I was talking about deciding whether I should talk to you about cis and transforms, and it's like um, too much. We don't have enough time, and it's too much complication. I usually don't talk about it. Some semesters, if we hit this a little bit earlier in the semester, and we're in person on campus, I will look at that, but not this semester. So your example though here uh, of your uh, ketone that has the simplest structure, which is where we'll have one carbon at each of those R spots. With the obligatory hydrogen stuck out here. This is acetone. Again, when you might be more familiar with acetone than formaldehyde as far as having actually used it, because if you've used fingernail polish remover ever, you've used acetone. Um, so that's an example. But again, this is what you're looking for. Is you're looking for this. If you see this structure right here, uh, you have an aldehyde or a ketone, one or the other. Okay, and then what makes the difference between the aldehyde and the ketone is what's here. Okay, if this is a hydrogen, you've got an aldehyde. If it's a whole nother set of carbons, or one carbon or more on this side as well as on that side, then you've got a ketone. Next grouping is organic acids. It's often referred to as carboxylic acids. Um, these are acids derived from organisms, such as, again, also known as fatty acids. There's carboxylic acids. They contain a carboxylic functional group. And so general formula on that is RCOOH, but it is not written like that. That's deceptive how that's put out there, because we're trying to type it on a line basically. So again, if you refer to your little table that on the inside of your textbook, um, you're looking at a structure very similar to your aldehydes and ketones we just got through talking about. I think I can draw this here instead of going to a different page, but you've got get my pencil back. You've got a carbonyl group. Okay, so these are still carboxylic acids, so carboxyl, it's building on that. And then over here, you have the OH, the hydroxyl group basically added. So you can kind of see where this term comes from, carboxyl, okay, uh, carbonyl, hydroxyl, carbonyl, hydroxyl, carboxyl, okay. All right. So that is the structure you're looking for that distinguishes these from other structures. You see that attached on anything, any bunch of carbons, carbon chain, carbon ring, doesn't matter. You see that you've got a carboxylic acid, okay, or an organic acid of some sort. So this one will be discussed in your book. Oh, hey, yeah, I was going to mention that on the aldehydes. Some other aldehydes other than formaldehyde that you're probably familiar with are vanillin and citronella. Okay, those are more complex. They're in your book on 609. You can look at their structures. They're more complex than formaldehyde, obviously. And then ketones, your acetone, and then there are the more complex ones shown have to do with sunscreen and sunless tanning agents. They're in your book if you wanted to look at those. Those more complex things won't be on your test. At least you won't have to name them. Again, you recognize that the structure, what family does that structure fit into? Aldehyde, ketone, okay? So see, carboxylic acids, or I think the next chapter over then. Kind of going through these chapters really fast because I'm just hitting the highlights with you. Once you see the structures. So chapter 13, we have our carboxylic acids. And um, so the simplest of these kind of like with the formaldehyde and acetone, if we don't have a carbon here, we just look at our base carboxyl unit as our one carbon. Okay, and we put a hydrogen here. Okay, that's formic acid. Formic acid is found in ants. Okay, it's like ants. I think it's you can eat an ant, but if you eat too many of them, I think the formic acid can be a little upsetting to your system. I think the ants that bite, sting, that's kind of what is irritating is the formic acid. Methanoic. Okay, methanoic. So that's your alternate, your actual real name. Formic is the traditional. Methanoic follows the IUPAC naming practice. So we've got one carbon, so that's methane, and then all of your carboxylic acids take an OIC, OIC ending in, okay, methane, and then remove the E and put OIC, and then acid. Everything in this group will be called acid. Something acid, something oic acid. Okay, methanoic acid, ethanoic acid. Okay, ethanoic acid, by the way, is acetic acid. To draw acetic acid for you real quick, that would be coming over here and just simply putting our carbon there. Okay, ethanoic acid. And that's acetic acid is a common name that you would know it as, and that is, it's vinegar. Vinegar is like 5% acetic acid, and the rest is water. The vinegar you use, food, okay, but also ethanoic. Acid. Okay, 1, 2, ethane. Take the E off, oic, and then of course acid. Okay. All right, so and those are your carboxyl groups. Things can get more complex than this. Obviously, I'm gonna see if I can, I think I've got a picture or something next page, if I remember right. Okay, so here's your standard alkane hydrocarbon. What do we have here? 1, 2, 3, 4, 5. Name it. Pentane. Okay, and so here, 1, 2, 3, 4, 5. Pentanoic acid. What this little diagram here is trying to show you too is that this is hydrophobic. It's not going to associate with water. It's afraid of water, water fearing. This is a thing I'm building to because the whole point in learning about some of these structures right here, right now, is to get you into the organic molecules inside the cell. Okay, so uh, hydrophobic and hydrophilic, terms that it's kind of thrown around at you already, but when we get to cell membrane, plasma membrane, we're going to be talking about that a little bit more. So what we have here is, this one is hydrophilic, means water loving, and it's a ionized form of the acid. Right here you can see that there should be a hydrogen there, and it's not there. And by not being there, that allows this oxygen to have a negative potential, and therefore it's going to bond to something or be willing to bond to something. So it can um, uh, attached to water. Okay, there's these. It can form, uh, can ionize in water. All right, dissociate in water, not pull apart. Okay, the hydrogen is part of that. Yeah, hydrogen dissociation. We've talked about that briefly in solutions before we had to uh, leave for spring break and go and then not come back and go into this. So uh, you can maybe refer back to some of that too. But we're just basically, I'm wanting you to get the idea that some things just won't dissociate in water, holds to itself, will attract to maybe itself, but not water. And then you have things that'll dissociate in water and therefore can mix. We talked about that with sodium chloride as the simple case. Okay. Esters. Um, so esters have smell, and we've talked about some aromatic compounds that have smells too. But esters are a larger category, I think, larger of things that are more commonly encountered. Okay, these are going to be in foods and things. You're going to find these. They smell and taste are really, really closely related. You know that if you catch a cold and you can't smell anything because you're all stopped up, then you might be able to taste some food, but it usually tastes bland. Nothing tastes good, or only a few maybe really spicy things or something will taste in a way you can notice and enjoy them. And that's because you can't smell. Okay. So these words that, well, I taste, our taste buds should taste it. Yes, but the smell enhances that. Okay, so they're very closely connected to each other. So esters are things that uh, the characteristic odors of these also have tastes that are associated with those odors and smells, and you got to have both sometimes in order to be able to enjoy it as far as food goes. So our formula here is going to be uh, back to that carbonyl looking thing again. Okay, so this is a it looks like a carboxyl. All right, look inside your book cover. Looks like a carboxyl, but we're going to change it a little bit. So one of the things you might be noticing if you start looking at these structures, the patterns inside the back of the book, uh, is that where I started, I progressed. We kind of built. We got single bonds, we got double bonds, and then we got triple bonds, and then we went back to the single bonds and we circled them up, and then we went back to the single bonds. Well, we circled them and we put some double bonds in there. Then we went back to the single bonds and we started adding oxygens. Okay, an oxygen to make an alcohol, and then we added oxygens double bonded, and then we started adding. Okay, so I did that to try to show you base structures and how we build on base structures. Okay, so for here we've got a carbon and double bonded to an oxygen, so carbonyl group again. We have our oxygen that would make it a carboxyl group, but now instead of putting a hydrogen on it, we're going to stick another carbon over there. Okay, all right, and we can put another carbon over here or something. Hydrogen, let's see what the examples that you've got in your book for this are. I have no idea because I'm not on the right page. Um, let's see. Hmm, they really don't give you any like common ones you would have heard of, possibly even. Um, yeah, that's disappointing. I've got in my lecture materials at school, which I didn't bring home with me because it's like, oh, I've got that on the computer. Um, I've got examples. I've got some examples of some common esters and their uses. Flipping further back in the chapter. Yeah, just not find anything. Well, one I always like to laugh about, because it's common in some soda pops, is ester of wood rosin. Okay, so they've derived uh, an ester of some, who knows how many carbon structures are over there on that here. Okay, but it's going to have this basic structure. Ester, actually, I need to put this as an R. Okay, ester of wood rosin is in, well, it used to be at least in um, Welch's pineapple soda. Believe it or not, they had a pineapple soda. It was good. Um, there was something else. We found it in some of the fruitier type drinks and juices, these ester of wood rosin. Always made me a little bit, I don't know, nervous to drink it. It's kind of like wood rosin. Not sure about that. Uh, so anyway, that it enhanced the flavor. Okay, it's something I don't really know what the pure smell and taste of ester of wood rosin by itself is, but I always noticed that it was in these fruity drinks, the fruit punch and fruit pop type things. So, and I think of the Welch's Pops as only in the pineapple, which, you never, I don't know if they even make it anymore, but there for a while, you could find it. So, uh, it obviously has something to do with that type of fruity flavor, sweet, fruity. It either enhances it or it gives it completely. I'm not sure. So that's an ester that I found interesting when I discovered it. Okay, in my drink ingredients one time, and have never forgotten it. There's probably other better examples, and they are totally escaping me at this moment. But um, anyway, that's again the structure right here. Let me get a different color. That's the giveaway with this. If this is not a hydrogen, this is not an OH right here. Okay, you have an ester and not a carboxylic acid. Okay, so those the things to look for, the distinguishing factors to look for, to kind of memorize for the test and say, if I've got this, there's not an H, it's an ester. If I've got this and there's nothing here but an H is right there, then that's a carboxylic acid. If none of this is here and I've got an H, then that's going to be, that's just the carbonyl group. Okay, so by itself, um, you've got the aldehyde. Okay, so anyway, got those things to look for. That's the patterns that I want you to recognize. And that's, well, let's see, we got a couple more slides here and I'll call this little section good. It's probably gone on long enough by the time I get in here. So proteins, okay, getting in now to the organic molecules that make up living cells. That's my goal. Okay, so now we have proteins. Well, proteins are polymers. Okay, polymers are many parts. Poly means many, uh, of amino acids. And the amino acids are the monomers. Mono, single, one. Okay, monomers. So an amino acid, the structure of amino acid. That's something you need to know. It's in the back of your book, I think, in that table as well. Let's double check. Um, yes, well, the amine and the amides are there. And if you've got the amino group, then that is your, uh, on a carboxylic acid, then that's your, well, it's actually going to wind up being a ring. Okay. give you some examples here. I don't know that I've got any pictures. I'll probably have to draw it for you. Okay. So in the classroom, I have overheads I'd throw up on the overhead to look at these. But anyway, we'll make do. Okay. Amino acid uh, has a central C bonded to an H, an amino group, an acid group, and an R group. Do I have a picture? Hey, I do. Okay. So I somehow got this in here. From probably borrowed a different structure from what I've got for the overhead. But so here we are. We have a central carbon bonded to a hydrogen and an amino group. Let's look at that. Central carbon bonded to a hydrogen and an amino group. NH2 is your amine group, and if you're looking at the table in the back of your book, you can see that the amine group has dash NH2. Okay, and that the bond of the N bonds to the carbon, and then you have an N, and then nitrogen takes three, can take up to three bonds, we know. Okay, so there's our hydrogens. Okay, sloppy N, sorry, getting worse. Okay, all right, so we can see that's our amino group, central carbon, and the hydrogen. Okay, now what else did it tell us the structure needed to have? I can't go back because I drew. An acid group and then the R group. Okay, well, here's our acid groups. Yeah, carboxylic acid. Yeah, okay, so. And then this is the functional group. And this, the blue box, as you can see here, all of this is the same here and here and here. Okay, all of these are always the same. Whoops. So this is the structure to look for. You see this on anything on the test, and you know to label this as an amino acid. Okay, I just broke it down to parts here, but it's all the same. Okay, so that's your amino acid indicator. Okay, that this molecule is an amino acid. It's got that structure. Then the things in the blue box that are attached to it, that's what makes the amino acids different. Okay, these are the R groups. That's what these are. This is your R group. This is your R. This is your R. Okay, R. Could be anything. But this is the standard. This is the stable part of what gives its identity, is this structure here. Okay, so those are all of your amino acids are going to have that structure. And I just kind of skipped amides, and I'm pretty sure that I don't talk about them in this section. What the amide is the amide is basically um, a ketone with the second R group being replaced with your amino group. Okay, you've got the NH2 on that instead of the R structure. So let me get out of this, go back, and I'll show you that. Go back to my blank screen here. Where was that? Wow, it's back a ways, wasn't it? Okay, here it is. All right, so carbonyl group. some carbon-carbon chain thing over here. And then here, where in the ketone you'd have another R group, instead, we're going to have, I'm going to draw that neater. We're going to keep it all nice and straight. I think in your book they may have it actually in an angle, but we'll make that on the same line. Okay, so instead of having an R group over here, we have the amine group, and you can write as NH2. You can see it written shorthand as NH2, or again with the hydrogens shown in their molecular formula bonding out structural formula like that. Okay, that's the amide group. Okay, as opposed to the amine group. In the amine group, you don't have the oxygen. Okay, that's the difference there. It's just a carbon with your, in its simplest form, it's some carbon structure with a hydrogen attached, two hydrogens attached to the nitrogen. And so the generic way of writing that is to represent that C as the R. Okay, because it can be any number of C's. So amide, amine, okay, difference in those. And I think I do have one of each of those for you to identify on the test. Okay, and then there will be the actual full-blown amino acids. So we'll get back to that. So examples, these are 4 different amino acids. There's 20. Okay. The peptide bond is what holds these amino acids together to build a protein. So the amino acids are joined by a peptide bond. And that's why another name for protein is polypeptide, many peptide bonds. So a single chain of amino acids stick together as an example of a polypeptide. And here's a term that I think is very important, is denaturation. And this is an irreversible change in the shape of a protein due to the breaking of some of those bonds. So for the polypeptide, I've given you the example of a single chain, but they can be much more complex than that. That's called a primary structure amino acid. You can have secondary structure, tertiary structure, and quaternary structure amino acids that are folded back on themselves. They're pleated. They're yeah, very complex and in a sense kind of hard to imagine. Some of those accordion pleatings of sheets of chains, basically, folded back on themselves and bonded into sheets, and then the sheets are like I said, accordion folded, and it's kind of weird. And I think probably in your book somewhere they will get that's yet another chapter further on from where I stopped a minute ago. They kind of give you some drawings. Okay, I think that's it right there. What's that page? Yeah, 550. Okay, 552 actually is where you get into secondary structure, and it's talking about sheets and pleated sheets. Tertiary and quaternary structures are on 553 and 555, and they really don't give much of a drawing for that just because a 2D medium of paper, it's really hard, okay, to uh, do more than just describe it. Okay, so very complex. So I've mentioned before that these structures are held, these shapes are held together by the hydrogen bonding that occurs between the hydrogens on these building block molecules like our amino acids. And if you break those or disturb those hydrogen bondings, that can cause these proteins to lose the shape and the sheets can unfold and these alpha helix structures can spread out or they're kind of like little spiral strings, they can unspiral. uh, so when that happens, then the protein's shape is changed, and often that means it won't function the way it's supposed to function, especially enzymes that are supposed to bind to something. I talked about enzymes binding to our uh, to fat and breaking it down for us. If it fits in like a lock and key manner to its binding site of that other molecule that it's going to break down. And if it doesn't, enzymes or proteins, okay, they're specialized type of protein. If it can't fit to that site anymore, if its shape is wrong, it won't fit and it can't do its job. And pretty much all proteins function in some way where they fit something. If not an enzyme breaking something down, it's or maybe something that's triggering a process in your body. And again, if it can't fit where it's supposed to fit to trigger a process or to stop a process, it won't work. So denaturation makes a protein uh, unable to function. And it can also cause them to break apart. And if you break enough hydrogen bonds, they break apart into chunks of amino acids that aren't even proteins anymore. This is a key factor to the body's immune system being able to fight off a virus. Oh, hey, here's a timely topic. um, I don't know what the heat tolerance of the coronavirus is. I don't know if anybody knows that at this point. There's been talk about being out in sunshine and UV light helping and stuff like that. Uh, but for the flu, okay, for the flu virus, which is different, um, the body's own fever is high enough in most cases of flu strains to break down some of the bonds in the protein capsid. Okay, now you haven't had micro yet, so you don't may not know this. And if you sometimes students have had micro prior to this class, but usually it's taken afterward. This is kind of considered prerequisite for micro, but the an animal virus is usually a circular spherical shape. The first one you'll have to learn to draw is a bacteriophage, which is a weird little thing, looks like a lunar landing module like thing. Whoops, that's really getting sloppy. This type of structure. Okay, but that's not that's only a virus that infects bacteria. So now what we're talking about here, human ones, they've got these little spikes all off of. You got to imagine this is a ball, and these little spikes are protein things, and they attach to sites on our cell and fool our cell into taking them in. If you can break any of this down, break enough of these little protein structures here down, break the actual capsid here down into parts and start breaking this up, then the protein before it gets into your cell, like it's out in your bloodstream, then this virus is no longer viable. It won't be able to infect you and cause disease. So with the flu, you have a pretty low heat tolerance. Body temperature is perfect, but a little bit above that. And these um, hydrogen bonds, the hydrogen bonding between the protein structures start to break down. Um, and so denaturation can occur. So that's why under monitoring, allowing your body to run a little bit of a fever, okay, when you're sick is not a bad thing. It's your body's own immune response trying to work. You just don't want to let it get too high because high fevers are damaging to cell parts for the same reason. That high temperature causes denaturation of proteins, causes our enzymes problems, wreak havoc with the internal functioning of our own cell, not just a protein capsid on a virus. So uh, you've you got to monitor it. You got to be on top of it. Okay, but uh, why it's not necessarily a good idea to hit the Tylenol the minute you notice you've got a fever. A low grade fever, let it go. Okay. So going into nursing school, you may, depending on what information your instructors have read, you may get conflicting comments on that. People who conflict with me, but then they may conflict with each other. Different instructors may give you different information about that because there is an old school idea of fever is bad, and it is. High fever is bad, but low grade, let it run its course because it's probably working for us. So denaturation and why it's important for health. Okay, let me clear that off. That may be where I need to end here. Okay, this little drawing here, this is just how two amino acids can form a simple protein, a simple dipeptide. It's what's called a condensation synthesis. Uh, you get these two, the hydroxyl group here and the hydrogen here are going to be released, and a bond will form, as you can see, okay, between this nitrogen and this nitrogen, that carbon, and that's right here. That's the peptide bond. Leaving a hydrogen and a hydroxide floating around with nothing to do except pair up and make water. Condensation. See? So to synthesize a protein, actually, this is what we call the dipeptide because polypeptide protein, we need more than three, but a dipeptide, and you just keep doing this. You can do it here. Okay. You could do it there. You can just keep adding on like boxcars and get your single chain amino acids for a very simple protein. Okay. They can start branching. That gets more complicated. Okay. But that's your basic how a protein is made from the amino acid building blocks. And that's where I will stop this presentation because now we're going to get into uh, the components of the cell, and we're going to leave these structure classifications behind. Okay, but that is a good, I'd say 10 to 20, maybe, probably not quite as many as 20, but points on the next test. Okay. Yeah, it could be 20, come to think of it, because I do really give you kind of all possibilities and some things. So somewhere between 10 and 20 points on the final will be uh, be these structures and you classifying them. Okay. Especially if we include naming the alkanes, alkenes, alkynes, those, then I can definitely see this running probably about 20 points. So be sure and study those. Okay, I'll see you in the next one.